All right, before we get started, make sure that you have your identity sheet out so that you can look for formulas that we may use throughout the lesson. So this lesson, 5.2, is all about verifying trig identities. So first we're going to discuss the difference between an expression, an equation, and an identity, and then we're going to learn some different proof techniques for different identities that may arise. So just to recall, an expression is something like 4x squared plus 3. Okay, so you have some terms, but you have no equals sign. Okay, the next step up would be an equation. So let's say we had 4x squared plus 3, and that was equal to 21. So in this case, we have an equal sign. All right, so what we'd be looking for with this equation is certain x values as solutions. Okay, and lastly, we have this new word called an identity. So we've seen the Pythagorean identity, sine squared x plus cosine squared x is equal to 1. And identities are true for all x values. For any x value that you plug in, an identity should be true. Okay, so on your next slide, what you'll see is a list of steps that are helpful in verifying trig identities. Now I'm going to give you the #1 step, and that is, unfortunately, there's no one right way to prove an identity. And there's also no guaranteed first step. So often what you try the first time isn't going to work. Now, of course, these notes are laid out, so the problems that I have, what I do the first time is going to work. But when you're working on problems, don't get frustrated. If the first path that you take doesn't work, try a different one, okay? The main thing you have to remember, we're always working on one side of an equation at a time. We can't move things around like we do when we're solving equations. You work on the left-hand side or you work on the right-hand side, but never moving things from the left to the right. We're always looking for ways to factor expressions, add or subtract fractions together, possibly squaring out a binomial, or creating a single term in the denominator, which helps us to simplify. So the reason for prompt number 3, we have our formula sheet out, is because a lot of times we're looking for ways to replace one term with an equivalent form from our identity list. Okay, and if any of these steps aren't working, it's always a good idea to try converting everything in terms of sine or cosine. Okay, so our first identity, I'm going to work from the left-hand side first because it's more complicated. All right, so on the left-hand side, let's use the Pythagorean theorem, the Pythagorean identity, and replace secant squared theta with tangent squared theta plus 1, and then we're subtracting 1, and that's still over secant squared theta. All right, so we'll see if that's equal to the right-hand side by simplifying our numerator. So our 1 and our -1, those cancel out, and we're left with tangent squared theta over secant squared theta. And here we're going to split up tangent squared theta times 1 over secant squared theta. We'll apply our quotient identity, sine squared theta over cosine squared theta, which is tangent. And then that's multiplied by cosine squared theta, because that's the reciprocal identity. We cancel our cosine squareds, and we get sine squared theta. All right, so you can see our left-hand side is now way at the top equal to what we started with on the right-hand side. Therefore, we verified our identity. Our next example, again, the left-hand side is a lot messier than the right-hand side. So we have two fractions. In this case, we're going to try to find a common denominator. Now, before I get going, our variable is alpha It's just another Greek letter. It's just like theta or x or just any variable that we use to denote the angle. Okay, so my first step is let's get a common denominator. All right, so we've got 1 times the denominator of the right term, which is 1 plus sine alpha. And then we're adding 1 times the denominator of the left side, 1 minus sine alpha. And that's all over 1 plus sine alpha times 1 minus sine alpha. Okay, still working with the left-hand side. Our positive sine alpha and our negative sine alpha are going to cancel out, and we're left with 2, 1 plus 1, 2 over 1 minus sine squared alpha. Okay, so what we're doing is we're combining our numerator and foiling the denominator. Now we foiled the denominator because once we see that we foiled 1 minus sine alpha and 1 plus sine alpha, we get the Pythagorean identity, which is 1 minus sine squared alpha. So we can write that as cosine squared alpha. And finally, we're left with 2 times secant squared alpha. And that is going to be equal to what we started with on the right-hand side. Right, 2 secant squared alpha. Okay, so it cut off a little bit, but using our reciprocal identity. Our next example has 2 binomials on the left-hand side, tangent squared plus 1 times cosine squared minus 1, and that's equal to negative tangent squared x. So in this case, we can use 2 different Pythagorean identities. First of all, tangent squared x plus 1 we know is equal to secant squared x, and cosine squared x minus 1 is equal to negative sine squared x. We saw that in the last section. And then now let's start combining. We'll use the reciprocal identity for secant squared, which is 1 over cosine squared x. And we're multiplying that by negative sine squared x. If we write this all as one fraction, we get negative sine squared x over cosine squared x, which we should know using our quotient identity that that's negative tangent squared x. All right. In this case, this one was a lot shorter. The left-hand side and the right-hand side now match. They're both negative tangent squared x. Our next example, example 4, is going to be a little bit trickier to solve. So you can see we have a tangent, a cotangent, a secant, and a cosecant. So there's really no identities that come to mind that deal with all 4 of those trig functions. So the best place to start in this problem is converting everything in terms of sine and cosine. Okay, so let's go ahead and do that. Tangent of x would be sine x divided by cosine x. Cotangent is just the reciprocal of that, so cosine x over sine of x. This would be equal to 1 over cosine x, which is secant x, times 1 over sine of x. So let's see if we even need to do the right-hand side. We'll wait and see if that was necessary. On the left-hand side, let's get a common denominator. So the left becomes sine x times sine of x plus cosine of x times cosine of x all over cosine x times sine of x. All right, why did we do that? Well, now you can see in the numerator we've got sine squared x and we've got cosine squared x. And since we're adding them, over cosine x times sine of x. So if we add sine squared x plus cosine squared x, we get 1 based on our Pythagorean identity. So that's a very common identity that we use. Now we have 1 over cosine x times sine of x, which is equal to what we got to after step 1 on the right-hand side. Okay. So often when you have a bunch of different functions that you can't seem to find an identity to relate them, the best place to start is writing everything in terms of sine and cosine. All right, our next example. We're going to verify the identity. And in this case, I look to the right-hand side, which looks a little bit messier. We have fractions, and we also have subtraction in the denominator. So what we want to do is let's multiply by the conjugate on the right-hand side. So if we have 1 minus conjugate, 1 minus sine of y, we're going to be multiplying the right-hand side by 1 plus sine of y on top and the bottom. Okay, now the reason we do that, we'll leave the numerator alone. We can distribute out the cosine if we want. So cosine y plus cosine y times sine y. And on the denominator, we see this difference of squares popping up. 1 minus sine and 1 plus sine turns into, if we FOIL it, 1 minus sine squared y. And then we can apply our Pythagorean identity to the denominator and turn that into cosine squared y. Okay. My next step, I'm going to break up the fraction on the right side into 2 separate fractions. So let's separate. We've got cosine of y over cosine squared y. And then we've got cosine y times sine y over cosine squared y. And in each of these terms, we can simplify by reducing the power. Reducing the power of cosine. 1 over cosine y is our first term, and our second term, we can cross out cosine y, and that's squared, and we get sine y over cosine y. And if we go one step further, by using our reciprocal identity, we get secant of y plus sine y over cosine y is tangent of y. And at that point, we're done. We've verified that it matches the left-hand side that we started with. All right, 3 more shorter examples. In this next example, you can see that the left-hand side and the right-hand side look, I would say, equally messy. So let's work on both sides. But don't forget, we can't move anything across the equal sign. Whatever's on the left-hand side has to stay there. Okay, so work on both sides at the same time. So the left-hand side, I'm going to use the Pythagorean identity. And because I notice that I have cosecant on the bottom, and because cotangent squared relates to cosecant, I'm going to turn cotangent squared into cosecant by using the Pythagorean identity. So here I get cosecant squared theta minus 1 over 1 plus cosecant theta. That's my left-hand side. And my right-hand side, I'm going to separate into 1 over sine of theta minus sine of theta over sine of theta. Okay. So I separated. My left-hand side, I'm going to factor out the top because it's a difference of squares. So I get cosecant theta minus 1 and cosecant theta plus 1 all over 1 plus cosecant theta. And on the right-hand side, 1 over sine of theta gives me cosecant theta. And sine theta over sine theta is 1, so it's a negative 1. It's as easy as canceling out our cosecant theta plus 1 terms. And now we verified that cosecant theta minus 1 equals cosecant theta minus 1. All right, so it is possible to work on both sides throughout the problem, but make sure you do not move terms from one side to the other, because then we're no longer verifying the identity. All right, our last two examples involve factoring. So this example, the right-hand side, we notice that there's a tangent squared x in common. So let's factor out the tangent squared x and see what we're left with. All right, so we're left with a secant squared x minus 1. And based on our Pythagorean identity, that would give me tangent squared x times tangent squared x. And if we combine those, in total, we have tangent to the 4th of x. All right, and that is what we started with on the left side. So that one's good to go. The next factoring example, very last one, is sine cubed x times cosine of the 4th x. And then on the right-hand side, I notice the only term that's in terms of sine is this last term, sine of x. So what I want to do on the left-hand side is let's turn the sine cubed x into sine of x times sine squared x, and then we still have our cosine to the 4th of x. All right. Now the reason I did that was I know there can only be one sine of x term, so I'm going to replace this middle sine squared term using the Pythagorean identity. Okay. I'm going to replace that term to be 1 minus cosine squared x times cosine to the 4th x. And you can see we're getting somewhere now. We've got sine of x. If I distribute my cosine to the 4th of x back into the parentheses, I would get cosine to the 4th of x minus cosine to the 6th of x. And that whole quantity is multiplied by sine of x, which you can see is equal to the right-hand side of my equation. Okay, so that's all I have for you today with this lesson. There's one more identity for you to try on your own before coming to class. Just a quick recall. Proving, right, or verifying an identity is not the same as solving. Okay, so we're not solving equations, we're just proving if one side is equal to the other. So try out that problem on your own and come with questions.